quadrillion years. That is how long a single dead star needs to finish cooling into the coldest thing the universe knows how to make. Not a million, not a billion, a quadrillion, a 1 with 15 zeros behind it. The universe has been alive for 13.8 billion years, and that sounds like forever until you lay it against this number and watch it vanish to almost nothing. We are not part way to the first black dwarf. We have barely stepped off the porch. Here is the part almost no one says out loud. A black dwarf is not an object sitting somewhere distant, waiting for a good telescope to find it. It is an object that has never existed anywhere, that cannot exist yet, held back by a stretch of time the universe has not lived long enough to cross. Tonight we follow the dead star that becomes one, the strange crystal hardening in its core, the date the first one finally arrives, and the last light the cosmos will ever throw into the dark. If slow, grounded, deep-time science is the reason you are here, a like or a subscribe helps these videos reach more quiet, curious minds. Now, let us begin. You already know that stars die. You have seen it. The expanding shell of fire, the flash that briefly outshines a galaxy, the violent ending of something that burned for 1 billion years. That is the picture most of us carry to bed. Death as an explosion, loud, sudden, finished. The sun will do none of that. There will be no blast, no shockwave racing across the planets. When the sun runs out of fuel, it will come apart slowly, almost gently, and it will take its time about it. In roughly 5 billion years, the sun will swell into a red giant, wide enough to swallow Mercury and Venus and scorch the Earth down to bare rock. Then, bloated and unstable, it will do something quieter than any explosion. It will let its outer layers drift away. Picture that, because it is softer than you would expect. The outer atmosphere of the dying sun simply lifts off into space, peeled away in slow glowing rings that hang in the dark for a few tens of thousands of years before they fade. Astronomers call those rings a planetary nebula, an old name with nothing to do with planets. The ring nebula in Lyra is one, a luminous loop about 1 light-year across. The Helix Nebula is another, near enough that long exposures show it as a vast pale eye staring out of the black. Each of them is a star caught in the act of dying, and the bright point at the centre of each is the thing we came here to follow. When the rings have drifted apart, the bare core of the sun is left behind, exposed, alone. That core is called a white dwarf, and it is stranger than the explosion you were imagining. Take what is left of the sun after the outer layers blow away, somewhere near half of the star's original mass, and crush all of it down until it fits inside a ball no larger than the Earth. A whole star's heart, folded into the volume of a single planet. At that point, the matter stops behaving like anything you've ever touched. Not gas, not quite liquid, not solid in any way you would recognize. Something pressed far past the rules of ordinary stuff. Try to lift a piece of it. Reach in, scoop out a thimbleful, set it on the table in front of you. That thimbleful weighs more than a loaded truck. You cannot nudge it. No machine in your house could, and it would not stay on the table at all. It would punch through the wood, through the floor, through the foundation and the bedrock beneath the house, and keep falling, because nothing in your world was built to hold that much weight gathered into that little room. The gravity tells the same story from the other side. Stand on a white dwarf if you somehow could, and you would weigh something like 100,000 times what you weigh right now, enough to press a human being into a film, thinner than paper in a single instant. The pull is so fierce that the whole surface is smoother than anything human hands could make. A bump taller than a fraction of a millimeter gets dragged flat. No mountain can stand there. Tens of thousands of times the grip that holds you to your chair, smoothing an entire dead star into a sphere. Sit with that for a moment. This is not a creature from theory. We can see them. The nearest one we know well is Sirius B, the faint companion to the brightest star in the night sky, about 8.6 light-years away, close enough that its light reaching you now left around the time a child starting school this year was born. Sirius B carries about the mass of our Sun inside a body the size of the Earth, and its surface still burns near 25,000 degrees, more than 4 times hotter than the face of the Sun you saw this morning. We did not even find it by its light, we found it by its weight. In 1844, the astronomer Friedrich Bessel watched Sirius wobble as it crossed the sky, tugged by something heavy and unseen, and he called the hidden companion years before anyone saw it in 1862. A dead star announced to the world by its pull before it was ever caught by its glow. That is how solid these small things are. And this is the common fate, not a rare one. Something close to 97 of every 100 stars in the galaxy, the Sun firmly among them, are bound for this quiet ending rather than the rare violent burst of a true giant. There are already billions of white dwarfs scattered through the Milky Way, with more forming in every age. The sky is filling slowly, star by star, with cooling cinders. Every one of them is walking the road we're about to walk. What sits inside that cinder matters for everything that follows, so name it now. The core of a white dwarf is mostly carbon and oxygen, the burnt remainder of the fusion that kept the star alive for billions of years. The star spent its whole life turning lighter elements into these two, and when the fire failed, this was the ash that could not be burned any further at the temperatures the star could reach. Carbon and oxygen, crushed to that impossible density. Hold the two names lightly. They come back at the very end of tonight, and they come back changed. Sirius B is not alone either. Meet Van Maanen's star, the nearest solitary white dwarf to us. A dead core drifting on its own, about 14 light-years away, found by the astronomer Adrian Van Maanen in 1917. No bright companion beside it to give it away by its tug. Just a faint, dense, slowly cooling remnant, one of the first of its kind ever recognized for what it was. It has been cooling for a very long time, and it is still warm enough to pick out across 14 light-years of empty space. That single fact, a thing that has been dying for ages and is still glowing, is the whole problem of tonight in miniature. Before we follow the cooling down, notice how brief the spectacular part is. The planetary nebula, the glowing ring we just described, lasts only a few tens of thousands of years before the gas disperses and fades. Set that against a cooling time of a quadrillion years, and the ring is less than 1/10,000,000,000th of the white dwarf's total lifespan. The fireworks are the footnote. The long, slow cooling is almost the whole story, and it is the part almost no one pictures when they imagine a star dying. If you were approaching the dying sun as it shed those rings, you would pass through something like a thin warm fog, a cloud of gas that was recently the outer layers of a star, lit from within by the core at the centre. The further in you went, the hotter the light from that core, the colour shifting from visible into ultraviolet, the core itself blazing near 100,000 degrees, flooding the shed gas until it glowed. And at the centre of it all, smaller than the Earth, the bare core itself, pouring out energy it can never replace, already beginning the longest wait in nature. It helps to slow down inside the sun's last bright act, because it would be a strange thing to witness. If anything were left on Earth to watch, the end would not bring darkness. It would bring the opposite. Across a few 100 million years the sun would swell and redden, until it filled a quarter of the sky, a vast dim furnace where a small white disk used to hang. The oceans would be long gone, boiled off into space. Then, almost gently, the bloated star would begin shedding its outer skin in glowing rings, and for a few tens of thousands of years the dying sun would wear a halo of its own making before the rings drifted apart and faded. What is left when they clear is the core, the white dwarf, the thing none of this was ever really about, until now. And none of it is a fate the sun could dodge. We read its future straight off its mass, and the sun sits comfortably in the range of stars that end as white dwarfs, well under the line where a star dies in a true supernova instead. The sun is already about 4.6 billion years old, a little past the middle of its life, which means it is now nearer to becoming this strange, dense object than it is to its own birth. The change is not a maybe. It is scheduled, set so far past any date a human calendar could hold, that we get to treat it as a story instead of a warning. There is one more strange thing about these objects, and it runs against every instinct you have about size. Add mass to an ordinary thing and it grows. Pour more water into a balloon, and the balloon swells. White dwarfs do the opposite. The more mass one carries, the smaller it gets, because the extra weight presses the crowded electrons even harder and packs the whole body down tighter. A white dwarf near the 1.4 limit is no larger than the Earth, while a lighter one can be noticeably bigger. So the heaviest dead stars are the small ones, and the lightest are the large ones. It is one of the few places in all of nature where adding more makes a thing shrink, and it is a clean fingerprint. One more way we can read a white dwarf for exactly what it is from light years away. So a white dwarf is not cold, not at first. By the heat of its surface, it is one of the hottest objects in the universe, a leftover core still pouring out the stored warmth of the star it used to be. And here the strangeness turns into the whole point of tonight. It has no way to make more. The fire is out. The fuel that ran the star for billions of years is spent and gone. Everything it will ever give, it already holds. From the moment it forms, with nothing left to draw on, it does one thing and only one thing, from then until almost the end of time. It cools, that is all. Every white dwarf in the sky is a star that has already finished its life, and is now leaking warmth into the dark with nothing to replace it. It is not dying. It already died, the instant the fuel ran dry. What we see as a glow is only the heat of the body escaping, the way a stone pulled from a fire stays warm in your hand long after the flames are gone, and the sun is bound for exactly this. Not a blast, not a grand ending, a coal. The sun will not die in fire. It will end as a coal the size of a planet, glowing for a while, then less, holding the memory of its heat far longer than any mind can hold. The white dwarf is the doorway. The cooling is the road through it. To understand why the thing on the far side does not exist yet, you first have to understand what keeps the white dwarf standing at all. The word black does a lot of work, and your mind reaches for what it knows. So you reach for one of two things: a black hole, a pit in space that swallows light, or a cinder, a burnt lump of slag drifting in the dark. Neither guess is foolish, neither guess is right. A black dwarf is not a black hole, and the gap between them could not be wider. A black hole is matter crushed so far past every limit that space folds shut around it, and no light can ever climb back out. It is a wound. It is hungry. A black dwarf is almost its exact opposite. Nothing is collapsing. Nothing is being crushed further. It is calm. It is stable. It gives off no light for one plain reason, which is that it has finally lost every scrap of heat it once carried. The black of a black hole is the black of crushing gravity. The black of a black dwarf is only the dark after a fire goes out. One is a place where everything ends. The other is a place where nothing happens at all. And it is not a cinder either, though that word lands closer to the feeling. A cinder is ash, what is left when something finishes burning in open air. But a white dwarf, once it forms, is not burning in any ordinary way. There is no flame inside it eating fuel. which leaves a question that should bother you. If the fire is out, and the fuel is gone, and the thing weighs as much as a star, why does it not keep collapsing under its own enormous weight? Why does it not crush itself into a black hole the moment the heat that held it up is gone? To answer that, you have to meet one of the quietest rules in physics. Down at the smallest scale, the particles that make up matter obey a law. No two electrons may sit in the same state, in the same place, at the same time. They refuse to be crowded. Press them together past a point and they push back. And this is the strange part. They push back with nothing to do with heat, nothing to do with any force you can name from daily life, only the flat refusal to share the same room. That refusal has a name: degeneracy pressure. Inside a white dwarf, it is the only thing standing between a dead star and total collapse. Here's what that feels like in something you can picture. A train carriage at the worst minute of rush hour. Every seat taken, then the aisles, then people press shoulder to shoulder until the doors can barely shut. Now try to force one more person in from the platform. You cannot, and it has nothing to do with how strong anyone is. There is simply no room left. The electrons in a white dwarf are that crowd, packed to a far harder limit, holding a planet-sized body rigid through nothing but their refusal to be squeezed any tighter. That refusal has a deeper law behind it, worked out in the 1920s. Electrons obey what is called the exclusion principle, a rule that each one must hold its own distinct state, that no two may ever pile into exactly the same condition at once. In a loose gas, the rule almost never comes up, because there is room to spare and the electrons are nowhere near one another. But crush the gas far enough, as gravity does inside a dead star, and the electrons run out of empty states to move into. They are forced shoulder to shoulder against a law that flatly forbids them from sharing. The harder gravity presses, the harder that refusal presses back, and it presses back with no help from heat at all. This is the strange engine under every white dwarf in the sky. Not fire, not motion. A law about how small a space a particle is willing to share, scaled up until it can hold a star. You do not need to follow every step of this, only the edge of it, because the rule has an edge. Keep piling mass onto a white dwarf and you press that crowd harder. For a long way, it holds. But there is a ceiling on how much it can take, and we have measured it exactly. It was worked out in the early 1930s by a young physicist named Subrahmanyan Chandrasekhar, who did much of the arithmetic as a teenager on a long ship from India to England. The ceiling sits at about 1.4 times the mass of the Sun. Below that line, the crowd wins and the white dwarf stands. Push above it, and the crowd breaks, and the star collapses past the white dwarf stage into something far more violent. There is a human story folded into that number. When Chandrasekhar first laid it out, the idea that a star could have a mass beyond which nothing could hold it up was deeply unwelcome to the great minds of the day. One of the most powerful astronomers alive dismissed the young man publicly and cruelly, and the result was pushed aside for years. But the mathematics did not care who doubted it. The limit was real. It is now one of the most dependable numbers in all of astronomy, the line that decides whether a dying star settles into a quiet white dwarf or falls into something stranger. He was given a Nobel Prize for it, roughly half a century after he first worked it out at sea. The rule that quietly protects the black dwarf was nearly laughed out of the room. Keep that number close, because it returns at the very end of tonight. The 1.4 line is not only the gate a star must stay under to be born as a white dwarf, it is also the line that the rarest, heaviest of these dead stars will one day, after an eternity of slow change inside them, climb back up to. One figure, worked out by a young man on a ship, setting both the birth of these objects and, for a rare few, the manner of their death. It helps to know what waits on the far side of that line because it shows you what the limit is holding back. tip a white dwarf over 1.4 solar masses, often by stealing gas from a companion star, and it does not fade. It runs away. Fusion reignites across the whole body at once, and the entire star detonates in a blast bright enough to be seen across billions of light years. A Type 1, a supernova. Astronomers use these as cosmic measuring sticks precisely because they all go off at nearly the same brightness, fixed by that same mass limit. So the line is not a technicality. On one side, an object that can outlast the age of the universe. On the other, one of the brightest deaths there is, and the Type 1a is only one of the doors that open past the limit. Which one opens depends on the star you started with. A star much heavier than the Sun never stops at a white dwarf at all. Its core blows past the 1.4 line on its own. Degeneracy pressure surrenders, and the collapse does not halt at planet size. It crushes on, down to something denser still, a neutron star, a city-sized ball so tight that a sugar cube of it would weigh as much as a mountain. Heavier yet, and even that gives way, and the core vanishes into a black hole. So the family of stellar deaths is really a ladder set by mass. The great heavy stars fall the whole way down. Our Sun and the quiet majority like it stop on the first rung and stay. The white dwarf is where most stars come to rest. A black dwarf is only that rest, finished. The same exclusion principle governs the neutron star too, applied now to neutrons rather than electrons. Neutron degeneracy pressure holds that object up, the same quantum refusal at the next level of compression. And there is a mass limit for that one as well, somewhere around 2 to 3 solar masses, past which even neutron degeneracy fails and a black hole forms. So the whole family of stellar corpses is one rule applied at 3 different scales. Electron degeneracy holds the white dwarf. Neutron degeneracy holds the neutron star. Nothing holds the black hole. The white dwarf is the gentlest resting place, the first landing on the way down, and the one the vast majority of stars reach and stay. When the first real measurements of Sirius B came in, this density seemed flatly impossible. Early in the 20th century, the notion that you could pack the mass of the Sun into a ball the size of the Earth struck even great physicists as absurd, a sign that the numbers must be wrong somewhere. One leading astronomer of the day remarked that the message the companion of Sirius seemed to be sending, once decoded, amounted to little more than the word nonsense. But the numbers were right. Matter really can be crushed that far, held up by a rule no one had yet discovered. The white dwarf was the first hint the universe ever handed us, that the rules of ordinary stuff stop applying when gravity presses hard enough, and the hint took decades to believe. It is worth sitting with how strange this rule really is, because it has no clean echo in daily life. Press your hand flat to a table, and you feel firm resistance, and you might think the table is solid all the way through. It is not. The table is almost all empty space, and part of what stops your hand is this same refusal of electrons to share a state, scaled down to something gentle. A white dwarf is that refusal turned all the way to its limit, asked to hold up not a hand but the crushed heart of a star. The thing keeping a dead sun from collapsing is a cousin of the rule that lets you set a cup on a shelf, and none of this support leans on the star staying warm, which is the part that matters most for tonight. Ordinary pressure, the kind that holds up a living star or fills a balloon, comes from heat, from particles flying about and banging on whatever contains them, and it dies the instant things cool. Degeneracy pressure does not care about heat at all. It would hold the white dwarf up just as firmly at 1,000,000 degrees as at a hair above absolute zero. So the dead star can shed every last scrap of warmth, cool all the way to black, and not collapse by a hair. The support does not leave when the heat does. That one fact is the whole reason a black dwarf can exist instead of caving into a black hole the moment its fire goes out. Hold that against the black hole you first pictured, and the difference is total. A burning star holds itself up by effort, gravity forever trying to crush it inward while the heat of fusion shoves back out, and the instant the fuel runs low and the shoving stops, the star is doomed, because effort always ends. A white dwarf has stepped out of that fight. It is not holding itself up by working. It is held up by a law, and a law asks nothing of the thing that obeys it. The fire that lit your ancestors' nights came from a star straining against its own weight. The black dwarf that fire becomes will need no straining at all. It is not held up by burning. It is held up by a rule that forbids crowding, and a rule never gets tired, which finally tells us what a black dwarf is and clears away both your first guesses for good. Not a hole, not a heap of ash. It is this object, the stable, rule-bound, planet-sized core, after it has done the only thing it was ever going to do, lose its heat, all of it, until the glow is gone and only the cold, crowded, rigid body remains. Every textbook that lists the stages of a star is not lying to you when it stops at white dwarf. It is just stopping one stage early. The next stage takes longer than the universe has had to give. So the real question was never what a black dwarf is made of. We know that. The real question is the one in the title. If these things are so stable and the path is so simple, why has the universe not made a single one? The answer has nothing to do with what a black dwarf is. The answer is time and how much of it this takes. No fuel, no fire, no way to make new heat, and yet a white dwarf glows for ages. So ask the obvious question, slowly, because the answer is the hinge the whole night turns on. If nothing is burning inside it, how does it cool down at all? Where does the heat actually go? It does the only thing a warm object can do alone in empty space. It radiates. Heat leaks off the surface as light, the way a heated iron bar glows in a dark workshop, the way your own body throws warmth into a cold room without your noticing. The white dwarf simply sits there and shines its leftover heat into the surrounding black, one faint wave at a time, with nothing ever coming back. Nothing dramatic about it. It is the gentlest process you could imagine, and the gentleness is the problem. Worse, radiation is the slow door, and it is the only door open. On Earth a hot thing has help cooling down. The air carries warmth off it. Water draws heat from it. The ground conducts it away. A cup of tea is wrapped in a whole world eager to take its heat. A white dwarf is wrapped in nothing. A vacuum cannot carry heat away by touch, because there is nothing there to do the carrying. The only way out is light slipping off the surface into the void, and that is the trickle, not the flood. The dead star is trying to empty itself through the one channel that drains the least. Watch what that does to the colour, because the fade is something you could almost see if you had the ages to spare. A fresh white dwarf burns a fierce blue-white, the colour of the hottest flame, a surface that can sit near 100,000 degrees, more than 17 times hotter than the face of the sun. As it cools, it slides down through white, then a pale sun-like yellow, then orange, then a deep sullen red, the same colours an iron bar runs backward through as it cools in the dark, and then, past red, it slips out of the range your eyes can follow at all. It glows only in infrared, in heat you could feel on your skin but never see. Fainter, fainter, for ages with no end in sight. The light does not switch off. It drains away, colour by colour, over a span longer than the whole bright history of the universe. Take a breath here, because this is the moment the title starts to mean something other than what you first read. A black dwarf does not fail to exist because it is rare. It does not fail because it hides in some unsearched corner, or because our telescopes are too weak. It fails to exist because not one white dwarf anywhere has had time to finish the single slow task it was handed at birth. We know that for certain because we have gone looking for the dimmest, oldest ones we can find. The coolest white dwarfs ever detected, ancient cores that formed when the galaxy was young, have dropped to around 3,000 degrees at the surface. That sounds cold next to a star, until you remember that iron pours from a furnace at a lower temperature than that. These are the most thoroughly cool dead stars in existence, the current record holders for darkness. They've had more than 13 billion years to fade, almost the entire age of the universe, and they are still glowing a dull red. They're not even close. Put a date on that head start, because the bare number hides how old these embers really are. The oldest white dwarfs we can find began cooling when the Milky Way was still assembling itself, before the Earth existed, before the Sun had formed, when the universe held only a small fraction of the stars it holds now. They have done nothing but shed heat since a time so distant that everything you would call history, and everything you would call prehistory, and the whole age of the dinosaurs, and the slow building of the planet under your feet, all of it fits inside the most recent sliver of their cooling, and they are still warm, still red, still bright enough to find, to feel the slowness from the inside, walk the cooling curve, stand the whole quadrillion years up as a road and start walking it. The first stretch passes quickly under your feet, the star dropping from blue-white through yellow in what feels like brisk early miles. But the road keeps lengthening as you go. Each mile of cooling takes longer to cross than the last, the colour changing less and less, until you are walking for what feels like a lifetime and the ember beside you barely dims. Most of the road, by far, is that final flat stretch, where there is almost nothing left to give, and the star gives it more and more grudgingly, one faint shade of red surrendered across an age. You never reach the end of that road. No one does. The universe has not. This is the trap the whole title is built on. Take a rate that seems almost reasonable, a star cooling by a little each million years, and stretch it across a duration with no reasonable size, and the result is not a long wait. It is a wait that behaves like a wall. On Earth we use geology to measure deep time, the wearing of mountains, the drift of continents, the slow accumulation of rock layers. These feel like the outer limit of patience. A mountain range wears flat in around 50 million years. A continent takes a few 100 million to drift across an ocean. Both numbers vanish inside the bright age of the universe, let alone the quadrillion-year cooling. You could wear down and rebuild every mountain range on Earth thousands of times over, and still not account for a fraction of the weight. Every measure of slowness your world provides is far too fast for this comparison. The cooling of a white dwarf is not slow on any scale humans possess. It is slow on the scale of what the universe does next. Bring it home to our own star, because the sun is on this exact curve. Billions of years from now, after the red giant and the shed rings, the bare core of the sun will sit where the solar system used to be, a fresh white dwarf glowing fierce and blue-white. Then it will begin the same slow walk down we have been tracing. It will fade to yellow, the colour it shows you now, then to orange, then to red, then out of sight, and it will still not be a black dwarf. Long after the Earth is gone, long after anything is left to call it the sun, that cooling ember will go on shedding heat into the dark, a quadrillion-year task barely started. The warmth on your face this morning is an early withdrawal from an account that takes longer to empty than the universe has been alive. Put a timescale on where the oldest ones formed. 13 billion years ago, when the first white dwarfs were cooling in the infant galaxy, there was no Earth, no sun. The Milky Way had not yet settled into its familiar spiral. The very first stars, made of pure hydrogen and helium in the first few 100 million years, We're already dying and leaving dead cores, and those cores have been shedding heat into the dark ever since, across the whole history of every planet and every creature that ever existed, and they are still warm. The entire story of life is contained inside their cooling down, and you can put rough numbers on how little all of that moved the needle. A white dwarf cools by a few hundred degrees in surface temperature over every billion years, once it has dropped into the slower lower ranges. A few hundred degrees across a billion years in a star that still sits thousands of degrees above zero. At that rate, the remaining distance to truly cold is not just large. It is a number that makes the rate look almost motionless, which is why the wait is not merely long in some vague sense. It is long in a precise and measured and fully accounted for way, worked out from how quickly a compressed sphere at that density can radiate, with the result always landing near the same staggering answer: a quadrillion years. Give or take, distance only deepens the dark. Light spreads as it travels, thinning by the square of the distance it crosses, so a star that looks bright up close fades fast as you pull away from it. By the time these cooling embers lie scattered across the dead galaxies, even the few still glowing faintly would be far too dim and far too distant for any eye to catch. The fade is not only in the star, it is in the widening space between, swallowing what little light is left. Let that land before we go on, because it is the calibration that makes the rest believable. The whole life of the cosmos poured into a single object, and the result is a star's corpse still warmer than molten iron. That is how slow this fire burns out. The reason hides in a cruel piece of arithmetic. Think about how a hot thing actually cools. A cup of tea on the counter cools fast in the first few minutes, because it is far hotter than the room, and heat rushes out of anything in a hurry to reach balance. But the closer it drifts to room temperature, the slower it cools. The last stretch, from warm to truly cool, takes far longer than the plunge from scalding to warm. A hot thing sheds heat quickly. A nearly cool thing sheds it at a crawl. A white dwarf obeys that exact rule, stretched across spans that have no business existing. And the slowness compounds. Each step down the temperature ladder takes longer than the step above it, because a cooler surface radiates far less efficiently than a hot one. Halving the temperature does not halve the time. It multiplies it, again and again, until the final stretch from a dim red glow down to true black swallows the overwhelming majority of the entire quadrillion years. Over the next full billion years, more than 200 times longer than humans have walked upright, a cooling white dwarf will shed only a modest slice of its remaining warmth and barely shift its colour. The cooling is not slow the way a long afternoon is slow. It is slow the way a mountain is slow, except a mountain wears flat faster than this. So strip the white dwarf of the one thing you keep assuming about it. It is not a star slowly approaching death. The death already happened the instant the fuel ran dry. It is not cooling toward death. It already died. This is the body going cold, and the body is in no hurry at all. We have measured the rate. We know in broad strokes how this ends. And what comes next is that even this glacial pace is not the whole truth, because the cooling does not simply slow as it goes. At a certain point along the way down, the dying star reaches into its own heart and slows the clock further, on purpose. You probably assume that cooling, however slow, is at least steady. The star gives off heat, loses a little warmth, gives off a little less, smoothly down toward black, like a dimmer turned by a patient hand. It is the natural thing to assume. A cooling thing should cool in one direction, without surprises. It does not. Somewhere along the way down, a white dwarf does something almost no one outside of astrophysics has heard of. Its interior begins to freeze, not into ice, The core of a white dwarf is mostly carbon and oxygen, the leftover ash of the fusion that once ran the star, packed at that impossible density. As it loses heat, the loose, jostling atoms inside start to lock into place. They settle into a rigid, repeating pattern, a lattice, the same kind of order that turns water into a snowflake or molten rock into crystal. The dead heart of the star, very slowly from the inside out, is turning solid. This is not a guess pulled from theory. We caught it happening across a whole population of stars at once. In 2019, a team led by the astronomer Pierre-Emmanuel Tremblay used data from Gaia, a European space observatory launched in 2013 to chart the positions and brightnesses of more than 1 billion stars. The team did not watch a single white dwarf freeze, which would take longer than any civilization. They counted. Plot a huge crowd of white dwarfs by brightness and colour, and they should spread smoothly along the cooling curve, each sliding down at its own pace. Instead, the count showed a bulge, a pile-up, far too many white dwarfs bunched at one exact stage, like cars stacking behind something unseen on a clear road. And the stage where they stacked matched, almost perfectly, the temperature where theory said their cores should crystallize. The traffic jam was the freezing, caught in the act across millions of stars. It is worth pausing on the scale of that survey, because the scale is what made the discovery possible. Gaia did not study a handful of nearby white dwarfs. It measured the positions and brightnesses of well over 1 billion stars, building the most precise three-dimensional map of our galaxy ever made. Out of that ocean of data, hundreds of thousands of white dwarfs could be sorted by exactly how far each had cooled. Only with a crowd that large could a subtle pile-up at one stage stand out from the noise. A single cooling star would have told us nothing. 1 million of them, sorted and counted, revealed a delay no one had ever seen directly, written faintly across the whole population at once, and the freezing was not a story invented to explain the jam. It was the other way around. Physicists had predicted it decades earlier, from the known behaviour of matter at crushing density, and the predictions sat on paper for a generation waiting for an instrument sharp enough to test it. Gaia was that instrument. The pile-up was right where the math said it would be. A piece of physics worked out in theory, then confirmed across a galaxy of dead stars, more than 13 billion years after the first of them began to freeze. And the confirmation came not from drilling into one, which we cannot do, or from sending a probe, which we cannot do, but from the statistics of light. We measure what comes off the surface, compare the rates of cooling across a population of hundreds of thousands, and read what the data says is happening inside. What it says is, the crystals are there. They formed. They are stalling the cooling of billions of dead stars right now, in a process that started before the Earth existed and will still be running long after it is gone. Here is why the freezing matters, and why it stretches the wait even longer than the last section left it. When a thing freezes, it gives off energy. It is the reason a bottle of water left out on a hard winter night hangs stubbornly at zero for far longer than you expect, instead of plunging straight to the temperature of the air. Turning from liquid to solid releases stored heat, called latent heat, and that heat has to escape before the cooling can go on. So the white dwarf, right in the middle of trying to go dark, hands itself a fresh supply of warmth that it must burn off first. The cooling stalls. For a stretch measured in billions of years, the dying star is propped almost in place by the heat of its own freezing, glowing on while the rest of the universe ages around it. The Gaia data suggests this single stall can delay the fade by up to 2 billion years. Set that against Earth to feel it. 2 billion years is roughly the gap between the first simple cells on this planet and the first complex life. The dying star pauses on its road to darkness, for longer than it took life here to go from a single cell to something with parts. There is a strange beauty hiding in it, if you want to take it. The carbon in that crystallizing core, locked into a vast rigid lattice under crushing pressure, is arranged in much the same pattern carbon takes when we, on Earth, call it diamond. Meet BPM 37093, a white dwarf nicknamed Lucy, thought to have a core that is largely crystallized this way. A dead star, slowly turning into something close to a single planet-sized jewel, and using the very act of doing it to put off its own darkness for another age. The picture rests on models of how these cores behave, not on anyone ever drilling into one, but the shape of it holds. It is worth holding what that crystal actually is, because its scale has no match in any jewellery case. This is not a gem you could close your hand around. It is a crystallized core with the mass of a star, a single lattice of carbon and oxygen the size of the Earth, grown under a pressure that would flatten any diamond we have ever mined into a smear. A planet-sized crystal as heavy as the sun, forming in total dark, with no one to ever see it. And the only thing it does with its long, slow hardening is buy itself more time before the end. Try to picture the crystallization at two scales at once, because the contrast is what makes it strange. At the top, a crystal larger than the Earth. At the bottom, the change happens one atom at a time, one carbon or oxygen nucleus locking into its lattice position, releasing a tiny quantum of heat with each settling. Multiply that small heat by the number of atoms in a solar mass of matter, roughly 10 to the 57th, and the total energy released by the freezing of one white dwarf's core is equivalent to the entire output of every star now burning in the Milky Way across the next 10 million years. All of it released as slowly as possible, spread across billions of years, purely by atoms finding their place in a grid. That is not a coincidence. It is why the pile-up Gaia found was detectable at all. A microscopic quantum effect, multiplied by an astronomical number of repetitions, becomes a measurable pause in the cooling of an entire generation of dead stars. The very small and the very large meet in the middle, and what results is a delay you can read in a brightness map of the galaxy. And the freeze is not one clean event that finishes and lets the cooling pick up speed again. The crystal forms gradually from the centre outward, releasing its hidden heat in slow stages, and the newly solid core then clings to the rest of its warmth, in ways that drag the fade out further still. Every trick the dying star has, it uses, not by choice but by plain physics, to stay warm a little longer. The back half of the road to black ends up even slower than the front half, and the front half was already slow past all reckoning. That is worth holding on to when the rest of tonight drifts toward the unimaginable. The freezing is not a guess. We have seen its mark written across the sky. Everything that comes after it, the quadrillion-year fade and the explosions waiting at the end of time, is built outward from this one solid footing. The way you trust a long road a little more once you can see that its first few miles are paved and real beneath your feet. Let that settle before we go on. Notice what keeps happening to the thing we are chasing. It recedes from us at every step we take toward it. First, the road to black was a quadrillion years long. Then the road grew slower the farther along you walked it. Now the traveller stops partway down, hands itself a fresh load of heat to shed, and waits there 2 billion years before going on. The closer it gets to black, the slower it falls. The dark keeps moving away from it. This is the place in the night to step back from the physics and simply see where we have arrived. An object whose entire purpose is to finish cooling, built so that finishing is the one thing it can never do quickly, walking a road so long the universe has not completed a single example of the trip. If tonight is landing the way we hoped, A like or a subscribe carries this channel to more people who need exactly this kind of slow evening. Now we can finally do the thing we've been circling. Lay the number out in full and let it be as large as it really is. 13.8 billion years. The age of the universe. The whole span from the beginning of everything to the screen in front of you. It is, in a real sense, the largest number that means anything, because nothing that exists has ever lasted longer. Every star that ever burned, every galaxy that ever turned, every war and every love and every quiet afternoon in human history, all of it fits inside that one figure. It feels like a number with no flaw. Like a span you could call forever and not be wrong. Now set the black dwarf beside it. A white dwarf needs something on the order of a quadrillion years to finish cooling to black. The cleanest way to feel that is a single question. How many times would the whole history of the universe have to play out, end to end, before even one black dwarf could finish forming? Divide the quadrillion by the 13.8 billion. The answer is about 70,000. 70,000 universes, each as old as ours, laid one after another in a line, before the first dead star anywhere goes fully dark. There is a lot to hold in that, so build it into something your body can stand inside, because the raw figure slides straight off the mind. Compress the entire life of the universe so far, all 13.8 billion years, into a single second. One tick of a clock now holds the Big Bang. The first stars, the birth of the sun, the rise of all life, every empire, every person, this very breath, all of it inside 1 second. On that scale, how long until the first black dwarf? Not another second, not a minute. You would sit through nearly 20 hours of that same furious ticking, each second holding another full history of the cosmos before the first ember finally goes cold. Come at it a second way, to feel it from another side. Try to count to a quadrillion, one number every second, never stopping to sleep or eat. Counting to a single billion that way already takes more than 30 years, a whole adult life spent saying numbers without pause. To reach a quadrillion, 1,000,000 times further, you would count without stopping for far longer than the universe has existed. The number is not just big, it is the kind of big that breaks the tools we use for big. So write the universe's whole life as a fraction of the weight, and you get a figure that looks like a typing error. The cosmos has so far finished something close to 1,000th of 1% of the road to the first black dwarf. Not 1%, 1,000th of 1%. On any honest diagram of the full timeline, the entire history of everything up to this instant would be thinner than the line you drew to mark it. Try it one last way, as a calendar. Put the Big Bang at the first instant of January the 1st, and the first black dwarf at the last instant of December the 31st. Where does this moment fall, the one you're sitting in right now? Not in autumn, not in the first week. The whole history of the universe so far, every star and species and story there has ever been, finishes inside roughly the first 10 minutes after midnight on New Year's Day. The other 365 days, every hour of every one of them is the wait still ahead. We're not somewhere in the year. We're in its first few minutes, with the rest of the calendar stretching out blank and dark and almost entirely empty. There is one more way to feel how early we are, the most concrete of all. White dwarfs could not begin forming the instant the universe began. The first stars had to be born, live, and die before the first dead cause could exist, which means the very oldest white dwarf anywhere has been cooling for somewhere near 12 or 13 billion years at most. That is the largest head start any of them could have. And we have already seen where that head start lands a star. A dull red glow, still hotter than molten iron. The most cooled object the universe has managed to make, given the longest run it could offer, has not even left the part of the fade your eyes can follow. So lay the road out one last time and stand at the start of it. the quadrillion-year path to black running off past the horizon. The entire age of the universe, every star and every story inside it, is not the first town along that road, or the first mile, or the first step. It is the first thread of the first inch, a mark so small you would have to kneel at the start to see it. We're not on our way to the first black dwarf. We're still in the parking lot, and the engine has only just turned over. There is a reason that gap is so hard to hold, and it is not a failing of yours. Your mind handles small ratios with ease. The difference between 1 and 10, a day and a week, a short walk and a long one, all of that you can feel in your body. But it was never built to feel the difference between a billion and a quadrillion, because nothing in the life of a person, or even a whole species, ever once asked it to. Both simply register as huge and get filed in the same drawer, marked too big to matter. The work tonight has been to pry that drawer open and show that a billion and a quadrillion are as far apart as a single step is from a walk around the whole planet. So when the title says a black dwarf does not exist yet, it is not describing a thing that is overdue, or running late, or nearly here. It is describing a thing whose arrival is cut off from this moment by the widest practical gulf of time the universe has on offer, a gulf so wide the cosmos must first do almost everything else it will ever do before it can even start the final approach. The word yet does not point just over the horizon, the way it points when you say a kettle has not boiled yet. It points clean past the end of nearly everything. There is no human reference that survives the trip. 2,000 years ago the Roman Senate still met, and no language anyone speaks today existed in its current form, and that already feels like deep history. Line up every recorded year of human civilization, thousands upon thousands of them, and the line does not reach a millionth of the way across this gap. The mountains that look eternal to us were flat in tens of millions of years, and you could grind down and raise up every mountain range on Earth thousands of times over inside the wait for a single black dwarf. Whatever you reach for to make this number ordinary, the number is larger. That is the honest shape of the word yet. So say it plainly, because it is far too easy to soften, and it does not deserve to be softened. We picture the universe as old, even ancient, a place that has surely seen most of what it will ever see. Against the death of a single white dwarf, the universe is not old, it is newborn. It opened its eyes a moment ago and has not yet looked around. The universe is not partway to its first black dwarf. It has not begun. Now watch what that does to one small word in the title. Doesn't exist yet. That word yet is quietly the most reassuring word in the whole sentence. It promises the thing is coming, that it only needs patience, that if you simply waited, you would see one. And that is true in exactly the way it is true that you could count to a quadrillion if you only kept going and never died. The word yet is a human word. It grew up on a small warm planet where waiting meant a season, a harvest, a lifetime at the very most. Your brain treats yet as a promise of soon because for 300,000 years, soon was the only kind of waiting that ever mattered. That instinct served us well. It does not work here. Every context in which you use the word yet, it points at something you can still wait for. The kettle has not boiled yet. The bus has not come yet. The bread has not risen yet. Those yets all resolve within minutes, even the stretched yets of human life, the project not finished yet, the book not written yet, carry an implicit promise that the wait ends inside a human span. Stack 100 human lifetimes end to end, and you still have not covered a rounding error in the road to the first black dwarf. The word yet has no mode for this. It was not built with a mode for this. It stands in front of the gap and does its best, and its best is to sound like a small and patient delay, when what it is actually pointing at is the rest of time. The universe has completed roughly 1,000th of 1% of the trip. Express that as a fraction of a road, and it is less than 20 feet along a road the circumference of the Earth. Express it as a clock hand position, and the hand has not moved far enough to see. Every way you translate this fraction, it breaks the tool. Which is perhaps the only fully honest summary of where we stand. The universe is so early in the process of making its first black dwarf that no analogy we can reach for, no unit we have built to handle large numbers, survives the comparison intact. Stretched across this gap, yet is doing work it was never built to do. It is standing in for a delay so long that everything you will ever care about, everything anyone has ever cared about, happens and ends inside the first invisible flicker of it. Take what calm you can from the fact that none of this reaches out to touch you. The sun will become a white dwarf, yes, but not for billions of years, and its slow cooling will outlast you, the Earth, the solar system, and almost certainly the whole human story. The black dwarf is not a threat. It is not even an event you could attend. It is a destination so far down the road of time that the road itself and everything standing along it changes past all recognition before you could ever arrive. Which is the question that turns this from the story of one dead star into the story of the whole universe. If the wait is truly this long, what is left of the cosmos by the time the first black dwarf finally goes cold? Picture the night sky as it is now, stars past counting from a dark field. Behind them the soft pale band of the Milky Way, the blurred glow of hundreds of billions of suns. This is the universe in its bright age, the era of starlight, the only kind of cosmos any living thing has ever known. It feels woven into the meaning of the word sky. It is not. Stars are not refilled. Each one burns a finite store of fuel, and when the store is gone, it is gone. New stars do keep forming, born from the clouds of gas drifting between the old ones. But that gas is finite too, and worse, it is slowly being locked away. Every time a star dies and leaves a white dwarf, or a neutron star, or a black hole, a share of the gas is sealed inside a corpse that never gives it back. The universe is spending a fixed account and burying part of every withdrawal where it can never be spent again. Like any account drained and never refilled, it has a last transaction. Somewhere, someday, a final cloud collapses and lights the last new star the universe will ever make. The universe is in no hurry, and neither are you tonight, so hold the order of events because the order is the point. Astronomers who study the far future, building on a framework laid out by the physicists Fred Adams and Gregory Laughlin in the 1990s, place that last star birth roughly 100 trillion years from now. 100 trillion is already more than 7,000 times the present age of the universe. After it, no new stars, ever. The youngest still burning will be the smallest, dimmest kind, the red dwarfs, which sip their fuel so slowly a single one can glow for 10 trillion years or more. 1,000 times longer than our sun on a fraction of the fuel. They are the last lamps. And one by one, across an age beyond counting, even they go out. Hold the whole sequence at once because no single observer could ever watch it. First the great heavy stars die, the ones that blaze and burst spent in a few million years. Then the steady middle stars like the sun swell and shed and fade to white dwarfs across billions. Then, across spans longer than the whole bright age before them, the small red stars finally exhaust the last of their fuel and darken too. The sky does not empty all at once. It empties gradually, a fade no mind could hold, until the galaxies hold nothing but the cooling corpses of stars that ran out unimaginably long ago. That long dim age has a name. The astronomers call ours the stelliferous era, the age of stars, the bright brief opening chapter. After it comes the long degenerate era of cooling remnants, and it is there, in that far country of darkened galaxies, that the first black dwarfs finally finish cooling. After that, an even longer black hole era, when the only structures left are black holes slowly bleeding away into nothing. And finally the dark era, when even those are gone. We live in the first room of a house with almost endless rooms. The black dwarf belongs to the second. It helps to see why the gas cannot simply be reused forever. Each time a star dies, some of its material is flung back into space and can help build new stars. But a share is always sealed away for good inside the dense corpse left behind, where the pressures are too great for it to ever rejoin the cycle. A little more usable gas is locked up with every stellar death. Run that across enough generations and the supply of fresh, unburned material dwindles toward nothing, like a library where a few books are sealed behind glass after every reading until, in the end, there is nothing left on the open shelves to take down. The last star forms when the last loose gas is gone, and the era that follows is so long it makes the numbers stop behaving. The bright age of stars, the whole of it, runs a few tens of billions of years. The degenerate era of cooling remnants runs past 10 to the 40th power years. The black hole era after it, while the last black holes slowly evaporate, runs further still. Set the bright age beside those spans, and it is not a chapter. It is the first sentence on the first page of a book with more pages than your body has atoms. The black dwarf forms early in that book, and almost everyone who reads the title imagines it forming on the first page. Try to stand inside one of those darkened galaxies and look around. No bright stars, no glowing arms of gas, just the faint scattered red of the very last dwarfs, and then not even that. Cold remnants drifting on their old orbits, dark and silent, the wreckage of a galaxy that was once full of light, still turning slowly out of sheer momentum because there is nothing left to stop it. That is the address of the first black dwarf, a dead core in a dead galaxy under a sky with nothing in it. Stack the delays we have found and you can see why the weight is the size it is. The cooling is slow to begin with, because radiation is the only way out, and the slow way at that. The cooling slows further as the star fades, each colder step dragging on longer than the last. Then the core freezes and hands itself billions of years of fresh heat to shed. Then the new crystal clings to what warmth remains, and around all of it, the universe must first burn through its entire supply of stars, lock its gas away inside corpses, and go dark before the stage is even set. No single one of these is the whole answer. Each alone would already put a black dwarf out of reach so far. Together they multiply into a weight the universe has not begun to cross. There is a quiet symmetry in it too. The same slowness that keeps the black dwarf from existing is the slowness that will, one day, let it last almost forever. The weight and the permanence are the same fact seen from two ends. A thing that takes a quadrillion years to finish is, by the very same physics, a thing that once finished will sit unchanged for far longer still. The universe is not slow at making black dwarfs out of laziness. It is slow because the thing it is making is built to outlast nearly everything else there is. There is one more thing happening across all this time that makes the loneliness deeper. Space itself is expanding, and the expansion is speeding up, carrying the distant galaxies away from one another faster with every age. Long before the first black dwarf forms, every galaxy beyond our own small local group will have been swept so far off, racing away so fast that its light can never reach us again. The sky we can see will empty out, each surviving island of stars left marooned in a dark with no other islands in view. So the dead galaxy in which the first black dwarf cools will not only be starless, it will be alone, an unlit room with no window onto any other. Let me name what that image really means, because it is the layer the title keeps hidden inside its small quiet word. When you read "doesn't exist yet," You imagine the black dwarf arriving into a universe much like this one, only later. The same stars overhead, the same Milky Way arching across, waiting its turn in a cosmos that otherwise carries on. That is not what happens. The first black dwarf does not arrive into our universe at all. It arrives into a universe where the era of starlight is a closed and ancient chapter, where no new sun has been born in spans longer than the Bright Age lasted, where nothing is left with eyes to register that one more light has gone out. By the time the first one is cold, there will be no one left to call it dark. Try for a moment to stand at the very end of the age of stars, the last inhabited world, if there is one, circling the last red dwarf, untold trillions of years from now. Someone, or something, watching its small dim sun sink for the final time. No new star anywhere to replace it. No bright band of a galaxy overhead, because the galaxies flung their stars into the dark long before. Just that one fading red point going down, and after it nothing rising. That is the sky the first black dwarf forms under. Not ours. A last one. It is worth sitting with how strange an inheritance that makes the night sky we have now. The crowded, glittering dark overhead. The thing every culture built its myths and its calendars around, is not the normal state of the universe. It is a brief early flourish. A few billion years of unusual richness near the very start, before the long emptying sets in. Sailors steered by it. Whole religions were founded looking up at it. And it is a passing thing, a morning brightness the cosmos will spend the rest of forever slowly putting out. We did not arrive late to a finished universe. We arrived absurdly early, in the one short window when there was still a great deal of light to see by. There is a melancholy twist buried in that timing. A mind born into the deep dark of the far future, if such a thing could ever exist, would look out and see almost nothing. No other galaxies swept beyond reach by the expansion. No stars long since burned out. It would have no way to know the universe was ever full of light, that it once blazed with hundreds of billions of suns, that there was an age when the night sky was a crowded and glittering thing. The evidence would be gone, carried off, or burned out, or fallen dark. We're not only living in the Bright Age, we're living in the only age that can still see that the Bright Age happened. After us the light and the very memory of light fade out together. It is worth asking where the gas actually ends up, because the answer makes clear why the account cannot be refilled. Every white dwarf is sealed carbon and oxygen that was once a hydrogen cloud. Every neutron star is compressed iron and other heavy elements. Every black hole has locked its matter behind a one-way door. None of it goes back. The universe cannot recycle it, cannot start fresh, cannot borrow against the past. What built the Bright Age stays sealed in the corpses, and the supply of gas available for new stars shrinks with every generation. The Bright Age does not end all at once. It winds down, generation by generation, each wave of new stars smaller and dimmer than the last, like a campfire burning lower as the wood runs out, until the last log catches and nothing is left to add. Late in the Bright Age, before the final stars go out, the sky would already be noticeably quieter than ours. Fewer bright stars, more red ones, the grandest things burned out long since, the whole show drawing toward its last hour. The stars of our era, the bright sun-like ones that dominate the sky tonight, would by then be ancient history, as remote to late observers as the first generation of stars is to us. If there were anyone watching then, they would be watching a sky already clearly in decline, the universe unmistakably old and going quiet, the exit visible from any window. We live in the middle of the show, which is another way we have been almost impossibly lucky. The eras ahead have names and lengths, and the lengths tell the whole story in one line. The stelliferous era, our era, the age of starlight, runs a few tens of billions of years, call it 10 to the 11th. The degenerate era that follows, when cooling remnants outnumber living stars, runs to around 10 to the 40th. The black hole era beyond that, while the last holes evaporate away, stretches toward 10 to the 100th. Set 10 to the 11th against 10 to the 40th, and you are not comparing two large numbers. You're comparing a number to a number that has 29 more digits. The Bright Age is not a chapter in the life of the universe. It is a superscript. The universe's real existence, the long unlit middle, has barely started. So the wait is not empty time, a calendar to flip through until the right page comes up. The wait is the death of everything that makes the night sky a sky. The black dwarf is not the next thing the universe does. It is one of the last, formed in the ruins, in a cosmos already gone quiet and cold. Which leaves a strangely intimate question hanging in all that emptiness. When the first one does form, out there in the dark, what kind of star will it once have been? The answer is not the one you would guess, and it brings us, for a single quiet moment, back down to something almost small enough to hold. You expect the first black dwarf to be a star like our sun. A solid, respectable, middleweight star, the kind that fills the diagrams. It is the obvious pick. The sun is the star we know best, the yardstick for all the others, so surely its kind leads the way into the dark. It will not. Run back through what we learned about cooling, and one small fact falls out of it almost by accident. A heavier white dwarf is hotter, denser, holds more stored heat, and so it takes longer to cool. A lighter one has less heat to give and reaches the bottom sooner. So the race to be the first black dwarf is not won by the grandson-sized remnants, it is won by the runts. The first dead star anywhere to go fully cold will not be the corpse of a sun. It will be the corpse of one of those tiny, dim, slow-burning red dwarfs, the least impressive stars in the sky, whose remnants are the lightest and cool the fastest of all. There is a quiet irony in that. The red dwarfs live longest of anything, burning so patiently that one can shine for 10 trillion years, outlasting a sun-like star by a factor of thousands. They are among the last stars still burning when the rest of the sky has gone dark, and yet, once one finally dies, its lightweight remnant is the first to finish the long final task, the first to cross the line into true black, while the heavier corpses of grander stars are still faintly glowing behind it. The least of the stars goes first into the dark. The first black dwarf will not be a sun like ours, it will be the corpse of a lesser star. There is a kind of justice in the reversal if you turn it to the light. The universe spent its grandest effort on its biggest stars, the ones that blazed and burst and forged the elements that make planets and people. But the prize for reaching the final state first goes to none of them. It goes to a remnant so small and dim that, while it burned, almost no one would have looked at it twice. The order of the cosmos turns upside down at the very end. The faint inherit the dark first. It is worth naming the kind of remnant we mean, because we can already point to its living cousins. The lightest white dwarfs, the ones that cool the fastest, are the cores of small stars that never grew a heavy carbon and oxygen heart at all. We can see them now in our own galaxy, faint and low in mass, still ages from their end. The first black dwarf will be one of these, somewhere out in the dark, having simply outlasted the wait. Not a grand object, a small one. The kind of dead star that, in our bright young sky, would barely earn a footnote. Picture it, whenever and wherever it finally arrives. Not the proud remnant of a sun, ringed by the ghosts of the planets it once warmed. The small cold core of some forgotten little red star, resting in a dead galaxy inside a dark universe, having outlasted every brighter thing around it. the first object in all of history to finish the longest task in nature, and it is the corpse of a star that almost no one would have looked at twice while it lived. To be specific about the candidates, the first black dwarfs will likely be helium-core white dwarfs, remnants with masses somewhere below half a solar mass, the lightest dead stars the universe produces. These form from the smallest red dwarfs, which are too small to ignite helium fusion at all, so they leave behind a core made not of carbon and oxygen but of the helium they never got around to burning, lighter still, cooler faster. The rough threshold for the first finishers sits below about 0.5 solar masses, the very bottom of the white dwarf family by weight, and the universe makes a great many of them. Red dwarfs outnumber sun-like stars by at least 10 to 1, so the candidates for first are abundant. The race is won by the smallest and most overlooked, and there are many small and overlooked things waiting at the slow end of the starting line. And it will not announce itself. There is no flash when a white dwarf finally goes black, no last pulse, no signal sent. It simply stops giving off the faint heat it has been leaking for a quadrillion years, the way a held note finally drops below the edge of hearing. One moment, a thing the universe has never once managed to make. The next, the first of its kind, and nothing anywhere will be left to notice the line being crossed. And be honest about the timing, because here we are reading the far future off physics, not off anything we could ever observe. Whether the first black dwarf finishes at a quadrillion years, or several times, that depends on fine details of the smallest remnants that scientists are still working out. But the shape of the answer never changes. Small remnants finish first, heavy ones finish much later, and every figure on the table is so far beyond the present age of the universe that the gaps between them, vast as they are, make no real difference to anything said tonight. So it would be easy to end here, on something gentle, to say that at least these first dark embers will finally rest, that after the longest cooling in nature, the first black dwarf earns a stillness that lasts forever, a quiet reward at the end of an unthinkable road. It is a kind thought. It is the natural place to want to stop. It is also wrong. The black dwarf does not get to rest. Something is still moving inside it, slower than anything in the universe has ever moved, and given enough time, that motion does not lead to stillness at all. It leads to the single most violent thing the late universe will ever do. So picture the black dwarf, finished, cold, dark, solid, complete. The longest process in the universe over, the ember out, nothing left to do. The perfect image of an ending, a thing so thoroughly dead that not even a glimmer comes off it. Surely now it simply waits out eternity exactly as it is, a frozen full stop at the end of its stars-long sentence. That is not how it ends. Deep inside that cold crystal, something is still happening, and to see it you have to drop almost everything ordinary you know about how matter changes. We believe nothing fuses without ferocious heat, that you need the searing core of a living star to force atomic nuclei together against their will. But heat is not the only way. At the crushing density inside a white dwarf, the nuclei are jammed so close that, very rarely, they fuse through a purely quantum trick, slipping through the barrier between them by chance instead of by force. Stay with this part. It is the turn the whole night has been walking toward. To feel what that means, picture a ball resting in a valley with a hill on each side. In your world, the ball sits there forever unless something gives it the push to roll up and over. In the quantum world, the ball has a tiny, almost vanishing chance of simply appearing on the far side of the hill without ever going over the top, as if it passed straight through the rock. For any single nucleus, the odds are so small they are barely worth writing down. But inside a black dwarf there are more nuclei than you could ever count, packed shoulder to shoulder, trying over and over for span after span of time. given long enough, the impossible becomes merely rare, and the rare becomes routine. This is called pycnonuclear fusion, fusion driven by density instead of heat, and it never stops. It is hard to overstate how patient it is. For a given pair of nuclei, one such fusion might come only after stretches of time that already dwarf the cooling we spent the whole night marvelling at. The interior is not boiling with reactions like a living core. It is almost perfectly still, cold and rigid, with fusion creeping through it so seldom that calling it a fire would insult fire. Put rough numbers on the event rate to feel the patience required. In a living stellar core, fusion events happen billions of times per second in every cubic centimetre, a rate so high the fire is continuous and violent and bright. In a black dwarf, pycnonuclear events across the entire star, all the matter inside it, might total fewer per year than the beats of a single human heart in a minute. Trillions of tons of compressed matter, an entire dead star's weight, producing a handful of fusion events in a year, and yet given 10 to the 1100th power years, even that handful adds up to an iron core that kills the star. Patient is not the right word. There is no right word. Patient does not have a mode for this either, and yet, because the star sits there for spans that make a quadrillion years an eye blink, even this slow drip adds up. Drop by drop, across an ocean of time, the carbon and oxygen are carried toward iron. The iron core grows. This is the lesson the late universe keeps teaching, in case the cooling alone did not make it plain. Given enough time, slow is not the same as never. Things that would never happen on any human scale, that would never happen across the entire bright age of the stars, happen as a simple matter of course once the clock is allowed to run long enough. The black dwarf supernova is the purest case there is. It is the universe proving that, with enough patience, even the coldest, deadest, most thoroughly finished thing it knows how to make is not finished at all. And the number this demands is the kind that mocks every measure of permanence we own. We call a civilization long if it lasts 1,000 years. We call a species old at 1,000,000. We call the Earth ancient at a few billion. The fuse on the first black dwarf supernova is measured in none of those. It is measured in a figure you cannot write on a page without a tower of exponents. Stack every empire that ever rose and fell, every species that ever lived and vanished, every world that ever cooled and cracked, end to end across all of cosmic history, and you have not spent the first trillionth of the weight for that first flash. Hold the rarity in mind too, because it shapes what the end of the universe is actually like. Only about one black dwarf in 100 is heavy enough to ever reach this fate. The other 99 simply cool and sit and stay dark and whole for good. So the final act of the cosmos is not a great chorus of explosions, it is a near total silence, broken once in an unfathomable while by a single distant flare, and then closing over again. The exceptions light the dark. The rule is the dark. This is the work of a physicist named Matt Kaplan, who in 2020 followed that slow fusion to its end in a paper on what he called black dwarf supernovae. Label it clearly as careful speculation built on accepted physics, not as anything we've ever seen or could. Iron is the most stable element, the ash at the end of all fusion, the point past which squeezing nuclei together no longer pays. So a black dwarf, across this near-eternal span, is very slowly turning its own interior into iron. It is worth seeing why iron, of all things, is where this ends. Fusion is a stairway. Light elements fuse into heavier ones and release energy at each step. Hydrogen into helium, helium into carbon, on up the ladder. And that released energy is what powers a living star and holds it open against its own gravity. But the stairway has a top. At iron, the accounting flips. Fusing iron into anything heavier no longer gives energy back. It costs energy. Iron is the ash that cannot be burned, the bottom of the well, the most stable arrangement of nuclear matter there is. A living star that builds an iron core has, in that instant, run out of fuel in the deepest possible way, which is why the heavier stars collapse the moment iron forms in them. The black dwarf reaches the same dead end. It just gets there by a different clock. Not minutes of stellar panic, but a near eternity of cold, patient, one nucleus at a time creep. The carbon and oxygen we named at the sun's death, the ash that could not burn at any temperature a star could reach, climbs that last stretch of the stairway anyway, not by heat but by the blind patience of quantum tunneling, until it has assembled the very iron core that a living star only ever makes in its final seconds. The white dwarf spends forever becoming, by the slowest road imaginable, the one thing that destroys the largest stars in a heartbeat. And then, having built it, it does exactly what those stars do. It collapses. But not every black dwarf can reach this. The limit is 1.4 solar masses, and crossing it from the black dwarf side requires starting the cooling already close to the top. A white dwarf near 1.2 or 1.3 solar masses was itself the remnant of a relatively massive star, something in the range of 7 or 8 solar masses in its original lifetime. Only a star that heavy leaves a white dwarf that massive. Most stars, the Sun-like and smaller majority, leave white dwarfs well below 1 solar mass, which cannot climb anywhere near the limit no matter how long the pycnonuclear fusion runs. So the black dwarfs that eventually detonate are not only rare by virtue of the time required, they were, from the beginning, the remnants of unusual heavyweight stars, stars that were uncommon even in the Bright Age. This is why the figure of roughly 1% matters. Less than 1 in 100 white dwarfs was ever massive enough. The other 99+% sit too far below the limit, for the iron they will one day build to ever bridge the gap. They will simply cool. They will sit in the dark. They will be there, cold and intact, long after the last detonation has faded and the universe has run out of anything else to do. What we are describing when we speak of the last light of the universe is not a shared ending that all black dwarfs participate in together. It is the private exit of a rare few, separated from one another by silences with no measure, each one flaring alone, a few weeks of brightness in a dark that has otherwise lasted past all counting. Here is where it turns, and where everything earlier comes back at once. Recall the limit, the 1.4 solar mass ceiling that degeneracy pressure can hold. The heaviest black dwarfs, the rare ones just beneath that line, are converting their interiors to iron, and iron is heavier and packs differently than the carbon and oxygen they were made of. As the iron core grows, the object inches toward the limit it has rested safely below since before the era of starlight ended, and one day it crosses it. Degeneracy pressure, the quiet rule that held the star upright for an eternity, finally loses. The black dwarf collapses inward, and then it detonates. A supernova, in a universe that has been dark far longer than it was ever bright. Now the number, because it is the heart of the whole night. Kaplan's estimate for the first of these explosions lands near 10 to the 1100th power years. There is no way to fold that into a human shape, because there is no human shape large enough to hold it. The quadrillion years a white dwarf takes to cool, the number that has anchored this entire conversation, the number that already dwarfs the age of the universe 70,000 times over, stands to this new number roughly as a single heartbeat stands to that quadrillion. Not merely larger, so much larger that the words bigger and smaller stop meaning much at all. And they would not all come at once, which somehow makes it lonelier. The first black dwarf supernova near 10 to the 1100 years, the last perhaps near 10 to the 32,000, a number whose exponent alone holds more digits than this whole script. Across that span, the detonations would be spread so thin that the universe might sit in total silence longer than its entire first 10 to the 1100 years between one flash and the next, each one alone, each cut off from the one before by a dark with no measure. Picture just one, though no eye will be there to catch it, a cosmos gone fully black, no stars, no galaxies, no warmth anywhere, and then a single point blazes, the death flare of an iron heart that took longer to build than any mind could hold. For a few short weeks it pours out more light than a whole galaxy of living stars once did. A lighthouse with no shore and no ships, throwing its glare into an emptiness that forgot light an eternity ago. Then it fades. The dark closes back over the spot, and the wait for the next begins. And think about what that flare would briefly touch. For a few weeks, its light would race outward into a universe that has held no light for almost forever, washing over the cold, dark corpses of stars that died an eternity before, lighting the dead galaxies for the first and only time in ages, finding nothing alive to see it. A whole region of the cosmos lit by a single dying ember, the way a match struck in an endless cave throws a brief circle of light on walls no one has ever looked at, and then the match burns out, and the cave is dark again, and it stays that way for a span beside which the entire age of stars was a single afternoon. And notice what is doing the exploding. The carbon and oxygen we named at the sun's quiet death, the ash of the original star slowly turned across forever into iron, and then shoved past the very line that once kept it safe. Only the heaviest black dwarfs, perhaps the upper 1% by mass, ever reach this fate. The rest never do. But for that rare one in 100, the end is not a quiet fade. It is the brightest thing in a universe gone completely dark. And the line that has been waiting since the first section arrives on its own. The last light in the universe will come from the things we call dark. So the black dwarf, the coldest thing the cosmos can build, the end of a star, is not the end after all. It carries one final act folded inside it, on a fuse so long the universe must first grow old, then ancient, then unrecognizable, and then keep going for a span beside which all of that was less than nothing. The dark we have walked toward all night is not a resting place. It is a stage. And the last performance on it is the most violent thing the universe will ever do. And then what? After the last black dwarf supernova has flared and faded, after even the rare heavy embers have spent their single act, what is left? It is the natural question, and it closes the door on the far future. We followed the dark all the way to the point where it briefly catches fire one last time. The only thing left to ask is what remains when even that is over. What remains is the thing we were quietly looking for all along. The vast majority of black dwarfs, the ordinary ones, the cold remnants of stars like the Sun and smaller, never reach the mass to detonate. They simply persist, cold, solid, dark, scattered thin through galaxies that came apart long before, drifting through a universe whose other great structures are bleeding away. A black hole, the mass of the Sun, takes something like 10 to the 67th power years to evaporate completely, a number so large it makes our quadrillion a rounding error, and the largest black holes take far longer still. The black dwarfs outlast nearly all of it. They are among the last solid things the universe will ever hold. Put rough numbers on the contest to feel who wins. A black hole the mass of the Sun evaporates in around 10 to the 67th power years. A giant one, the kind at the heart of a galaxy, holds on until something like 10 to the 100th power years, a span so long that the previous number is a rounding error inside it. But both of those are clocks running down towards zero. The ordinary black dwarf has no such clock. Nothing is evaporating it. Nothing is fusing in it. Nothing is changing it at all. So while the black holes, The most extreme objects the universe ever built slowly boil away into nothing. The quiet dead stars simply remain, untouched, long after the last black hole is gone. The grandest things end first. The humblest thing, the cold cinder of an ordinary star, is what is left holding the dark together at the very last. If you're listening in the dark, let this one rest with you, because here is what the cold around them actually means. Space today still hums faintly with the leftover warmth of the Big Bang, a thin glow filling every direction you could point. By the time the black dwarfs have gone fully dark, even that ancient warmth will have thinned almost to nothing, stretched and chilled by the endless expansion, until the whole universe sits barely a hair above the coldest temperature there is, a cold so complete that it has a floor, a point past which nothing can get colder. At that temperature, everything we know surrenders. The air you are breathing would have frozen into pale solid long ago. Steel would shatter like glass at a touch. The very atoms slow until they barely stir. At temperatures a hair above absolute zero, every familiar substance has already surrendered. The air you're breathing right now, the nitrogen and oxygen in this room, freezes into a pale crystalline solid long before the universe reaches that floor. Helium, the last element that normally liquefies rather than freezes at ordinary low temperatures, becomes a superfluid and flows without friction over any surface it touches, obeying rules of motion that apply nowhere else in the ordinary world. Carbon dioxide becomes rock-hard frost. Methane becomes pale crystalline ice. The very hydrogen that once fueled the stars of the bright age sits locked into rigid lattices everywhere. At the absolute floor, the distinction between solid, liquid, and gas has long since lost its meaning. There is only matter, barely stirring, indistinguishable from the cold around it. A black dwarf at that temperature is not cold the way a winter morning is cold. It is cold in the way a thing can only be cold when everything around it is equally cold and there is nowhere colder to go. It has matched the universe. There is no longer a gradient between the dead star and the empty space, no sense in which warmth could flow from one to the other. It is as finished as a thing can be, and the universe around it is as finished as a universe can be. Even the last events of quantum field theory will have long since played out. In ordinary space, virtual particles flicker into existence and vanish again in pairs, billions of times per second per cubic centimetre. So briefly they cannot be directly seen, but real enough to affect measurable quantities. In the deep dark era, even those flickers have drained away as the available energy thins toward nothing. The universe stops stuttering with its tiny almost events. Everything goes still. Not the stillness of a thing that has paused, the stillness of a thing that is finished. A place where the laws of physics persist but have nothing left to apply to. The black dwarf sits at the centre of that stillness, unchanged, the last solid object in a universe that has run out of anything else to do. This is not the cold of a winter night. It is the cold the universe ends at, and the black dwarf does not fight it. It joins it. The black dwarf does not cool toward the cold any longer. It matches it. It reaches the same temperature as the empty space around it, and becomes, by every measure, indistinguishable from the void that holds it. There is no longer a line between the dead star and the dark. A moment ago it was a thing in the emptiness. Now it is the emptiness, with a slightly denser middle. That is the true meaning of the word black in black dwarf. Not dark against a bright sky, the way a bird is dark against the sun, black against black, cold against cold. A thing that has given up everything that once set it apart from nothing, until there is nothing left to tell the star from the space it floats in. It is the most complete kind of disappearing the universe knows how to do, and it does it to nearly every star that ever shone, given the one thing it has in endless supply: time, and the cosmos those embers sit in has by then simply run down. No new stars, no galaxies, no black holes feeding, no events. Only a thin scatter of stray particles and faint radiation spreading through a space that keeps expanding and cooling toward that floor. Nothing collides, nothing gathers, nothing forms. The universe does not end so much as it winds down, like a clock no hand will ever wind again, every part of it sliding toward the same cold sameness. And the cold is not the only thing thinning out. Everything is. The structured matter of the universe, given long enough, may itself come apart in the end, the particles slowly dissolving over spans that dwarf even the black hole era, until what is left is a thin haze of light and stray fragments with nothing to build. There are barely atoms left to freeze. The word cold stops even applying, because cold is something you measure against warmth, and there is no warmth anywhere left to measure against. This is what physicists mean by the heat death, a strange name for a state with no heat in it. Not a death by fire, a death by sameness. A universe so evenly spread, so perfectly run down, that nothing can ever flow from one place to another again, because there is no longer any difference between one place and another. In that final sameness, the black dwarf loses even its own identity. For most of forever, it was the densest thing for unthinkable distances around, a clear hard point in the thin dark. But as the dark itself thins toward nothing, even that distinction blurs. The line between the dead star and the empty space keeps softening, the way the edge of a fog softens until you cannot say where it stops. There was never a fence around it, only a gradient fading out, until belonging to the star or belonging to the void becomes a question with no answer. And somewhere in that long dissolving, your own sun is folded in, not as a special case. As one cold point among countless others, the carbon and oxygen that were once the burning heart of the star that grew the food you ate today, spread thin and dark, and no different from the rest. The most ordinary ending there is, shared by nearly every star that ever shone, including the one that will rise tomorrow morning if your sky's clear. There is something the physics does to you, once you've followed it this far, that it never warned you was coming. You came tonight to learn what a black dwarf is. A small thing, a piece of trivia about dead stars to file away, and the definition turned out to be a door, and behind the door was the whole future of the universe, and your own sun's place in it, and the strange fact that the most complete darkness the cosmos can make is also the one thing it has not yet had the time to make even once. You cannot unknow that now. The night sky will look a little different the next time you stand under it. Because every star you can see is on this road. Every one. The bright ones overhead, the sun that wakes you, the faint points at the edge of sight, all of them somewhere along the long path that ends in a cold, dark ember. The universe is still far too young to have finished even once. Then the embers go out and nothing in the universe ever happens again. And here is the turn that has waited under the whole night. We think of the dark as the gap between the things that matter, the space between the stars. But measured against the full life of the universe, it is the stars that are the gap. The bright age is a brief flicker at the very opening, a few billion years of light, and the dark that follows is the staggering rest of all time, by margins past counting. The black dwarf is not a strange object out in the darkness. The black dwarf, and the dark around it, is what the universe mostly is, and almost entirely will be. The light was the exception. We were born inside the exception, and mistook it for the rule. A quadrillion years. We began there, with that number, and with the small reassuring word the title hung beside it. Doesn't exist yet. We treated yet the way nearly everyone does on first reading, as a promise that the thing is on its way, that it only needs patience, that it waits just over some near horizon for its turn. The number has not changed. A white dwarf still needs roughly a quadrillion years to go cold. The universe is still only 13.8 billion years old. Not one black dwarf has formed anywhere, as true now as when we started. Nothing about the cosmos shifted in the while we spent together. The only thing that changed is the size of that little word, yet inside your own head, now that you can see what it has been standing in front of. The death of every star. The end of the whole bright age. The last explosions alone in the dark, and then a stillness with no event left to follow it. That word was never a promise that the black dwarf is near. It was the universe quietly admitting that it is not yet old enough, by a margin past all imagining, to have finished even one small dead star. The dark we have walked toward is not waiting for us at the end of the road. It is what the road is for. It is what the universe is slowly, certainly becoming, one cooling ember at a time, and the sun overhead is already walking that way. Thank you for staying all the way out to the cold end of time. If tonight gave you something worth keeping, a quiet subscribe helps more people find their way to evenings like this one. So the next time you look up, remember the light is only on loan. Every star you can see is paying out a warmth it can never earn back, drifting toward an ember it will not reach in any span you could name aloud. The black dwarf does not exist, not anywhere, not for a stretch of time longer than the universe has been alive, multiplied tens of thousands of times over, and then longer still. The yet is doing all the work.